Everybody doing? Great. I didn't get to stick around for I guess the award ceremony and the presentations on Sunday. So I'm just curious who made it to the final round. All right, and then who did anybody win prizes or whatever, the top honors? Okay, well, I don't know. They did? Yeah. All right. I would love to hear how everything went for everybody. But I had fun seeing you guys on Friday and Saturday. That was enjoyable for me at Data Fest, and but now we're back. And I'm finishing up your first homework assignment. You can expect to see that posted later today, and it'll probably be due in like a week from today. Okay, so that's the plan, and we'll go from there. So here we are. We're going to spend just some time wrapping up cross-validation. Okay, and so. We introduced cross-validation on Friday, and there was a tiny bit of confusion, and so I just wanted to provide a little bit of clarification. So when we did cross-validation, I said, you know, here's your entire data set, and you're going to fit a model to all but one data point. Okay, so if we have a data set of 4 data points, we fit a model to the remaining 3. Okay, and then we see how much error is there between that point and the point we left out. Okay, and we do that, and each of the 4 data points gets to be kind of the validation point. And so right here, you know, you fit it on the other 3, and you test the error. You fit it on the other 3, and you test the error. And you fit it on the other 3, and you test the error. And when you do this, you are going to just get a single cross-validation score for that model, which is going to be the mean of the cross-validation errors. You are not... you fit the same model n different times, and each time you measure the error, but you get one kind of cross-validation score for that type of model. Okay? So in our toy data set, we fit the linear model n times, 4 times, and we had n different cross-validation error values, and the total cross-validation score there would be the mean of those 4 values. So here, it's kind of the same diagram, and this time I've kind of printed additional information onto the screen where we've got, you know, these are the 3 points that were used to train this model. Here's the error, and the squared error there is 1. It was trained on these 3 points. Here's the remaining point, and the squared error is 1.65. Here's these 3 training points, and the squared error here is 1.653, and then here it was trained on these 3 data points, and the squared error is there. And so the total squared error of these is this, and if you divide by 4, because we had 4 different models fit, you know, our mean squared error is 1.33-ish. Okay, and so this is the score for using a linear model. And so after fitting a linear model n times, we would take that mean squared error as the cross-validation score. Then you could try a different model, say like a log-log model, or I don't know, whatever, a quadratic model or something. And then you would fit that other model, again, n times, calculate the squared error for each of those, each time you fit it, and then you're going to average all of those validation errors. Okay, and so by comparing the cross-validation scores, we can get an idea of how well the model predicts values that were not in the training data. Okay. And then I think I just briefly introduced the idea of k-fold cross-validation. Okay, so with leave one out cross-validation, each individual data point serves as the validation set. And so if you have, you know, n data points, you're going to have to fit the model n different times. Okay, and that can become computationally inefficient or expensive. And so with doing k-fold, you reduce the number of times you have to fit the same model. So, so we're going to look at the Olympic data, and we're going to split it into 4 random blocks. And each of those blocks will have a turn serving as the validation set. Okay, and every time we have a data point being the validation set, we're going to fit you know, a bunch of proposed models to just in order to compare their performance. Okay, so so we have 4 different blocks. So we have, you know, 4 different training and validation splits, and then for each one we're going to fit you know, linear, quadratic, cubic, and just basically polynomial functions of, you know, order 4, 5, 8, and 17, just for fun. Okay. And then for each of these things, we're going to calculate the total squared error of the model on the validation set. So just the points that were not used for estimating the parameters. And then we're going to find the cross-validation score by averaging the squared error for each model. And we'll compare the CV scores to select the model. So here's just kind of an overview picture. Again, we split the data into kind of 4 blocks. And then each time we're gonna use 3 of them as the training set and 1 as the validation set. And obviously you can do it with 10 blocks or whatever. And it's all but 1 are the training, and then the last one's the validation. Okay, so here's our Olympic data. And I set up the validation sets this way. Okay, so I said we have 28 observations in here. And then and I shuffle those using sample, and then we're just going to put 7 into each of these kind of blocks. Okay. And then here's just some generalized code for different n's and different k's that if you want to do. Okay. And because we're going to fit a model for each of we're going to fit 1, 2, 3, 4, 5, 6, 7 models on each validation block. I'm going to have kind of these 7 vectors to store the squared error values. And so when I do the cross validation, I've kind of coded this up manually here. All right, just so we can kind of see how it works. So I select one of these sets here. Okay. So we're going to loop through this 4 different times, and you know, so the first time, set A, the first set is going to be my validation set. Okay, and those are just the indices of which observations are validation. Okay, and so my training will be basically our data set where I subtract out the validation index, and my training response is the time where I've subtracted out the validation set validation indexes. Okay. And then the validation data set is valid X and valid T, where I just select the values in the validation index. I create data frames accordingly. Okay, I have the training data frame and the validation data frame. All right, and then and up here I fit model 1, which is a linear model between T and X using the training data. And once I've created that model, I use the predict function to see what values it would predict on the validation data. Okay, and so those will be my t hat values, and I compare the true validation values, validation $t, with the fitted values, the t hat. Okay, we take that difference and we square it and we sum it up. Right, and I do that, and then here's model 2, where I do t is predicted by kind of poly x2, okay? Again, we fit it, we use LM on the training data, and then once you have that model, model 2, you use predict on the validation data to get your t hat values. Okay, and you take that difference and you square it and you sum it up, and you get kind of the cross-validation thing that goes into the CV quadratic vector. Okay, and you just kind of continue this, and we had a whole bunch of different models. You know, model 1, 2, 3, 4, 5, the 8th order polynomial, and then I ran out of space, but there's also a 17th order polynomial in there. Okay, but we're doing the exact same thing. We fit the model on the training data, as however we've specified it. We use that fitted model to make predictions on the validation data, and then we compare the predictions with the actual values in the validation data, and then we square those up. Oh, I'm sorry. Over here, I should have divided by n being how many data points are in the validation set. Okay, so I have the sum of squared. Sorry, I'll fix this. This should be divided by n. I have 7 data points in the validation set, so we're going to get kind of an average squared error. Okay, should be a mean squared error here. Okay, so we're going to do this, and then we're going to get 4 of these values for each one. So here's just kind of an illustration of what this looks like. Okay, so here, after I've created my 4 blocks, I've just kind of chosen validation set C. Okay, and so the regular points, okay, are the training data, and then the red dots represent the validation data. Okay, and so we when we fit the data or fit the model, we remove the validation points, and we'll fit like a linear model on the remaining data. So this is the best fit line for linear regression. Okay, and once you have that fit model, you look back at the validation points, and you're going to measure the error, the residuals between the validation data and the line that you fit. Okay, so it's fit on the training data, and then you measure the prediction performance on the validation data. Okay, and so we're looking at kind of these residuals, and then we we square the residuals, and we take the average of we divide that by 7, and so the mean squared error on this validation set is 0.0369. Again, we go back to just the training data, so we remove the validation points, and now I fit a quadratic model on these points, and we want to say, okay, how well does this work at predicting the validation points? So on the validation points, we have these, okay? So it's the same validation points, and we're measuring the again, the residuals on these. Okay, so this is if you just focus your eyes on the red dots, you'll see that the red dots don't move. It's just the fitted line that moves. Okay, so this is the fit for a quadratic, and when we do that, the mean squared error is 0.0207. Okay. Same thing, now we're fitting a cubic model. Okay, so a cubic model looks like this on the training data. On the validation data, it looks like this. Okay, so same red dots, but the fit changes. Okay, and we basically do similar things for the other models. Okay, so here. With a 4th order polynomial, okay? So as we increase the complexity of our model, we can see we can start to kind of fit the training data even better and better and better, okay? But we're not interested in reducing just the errors in the training data. Okay, because we're afraid, what we don't want to do is we don't want to overfit the training data. So we don't want to fit just odd things that appear in the training data. We want to see how well does this do on data that wasn't included in the training data. And so it's a little bit subtle here with kind of the fourth order polynomial, and here's an eighth order polynomial. And you can see with the eighth order polynomial, we have the extra flexibility, so we can really fit this, this extreme point out here, okay? So this is kind of an extreme point, and the eighth order polynomial does a good job of reaching that, whereas, you know, the linear model is not able to kind of reach this point. The question is this truly the relationship that it actually exists in the population, okay? Or is this just kind of a weird fluke in our data? And probably looking at it, we would probably say this is just a little bit of a weird fluke. But anyway, this is the model that exists when you fit an eighth order polynomial. And we can kind of see that, you know, our we happen to get it right for some of these things, but we got quite a bit of error. The residuals are quite large for some of these other things, okay? And just to show how this works at the extreme, with a 17th order polynomial, I have a ton of flexibility, okay? And I can really minimize the training error, okay, or the error on the training data, okay? So I can fit this one exactly and this one exactly, and I can really kind of, quote, predict or minimize the error that exists on the data points that exist in our training data, okay? But again, you know, to see this kind of crazy relationship, this doesn't make sense that it would exist in real life, okay? And this is, the fact that this is a ridiculous fit is reflected when you say how well does it predict the validation points, okay? Because this is the fit model, and when we look at how it works on the validation points, we can see it's doing a pretty bad job for this point and a really bad job for this point, okay? Because according to, you know, this fit, you know, we should see a huge drop in the time in the year 2004 and then a huge spike in the time in the year 2008 or something, okay? Which clearly doesn't make sense, okay? Or in the year 2000 and something. So, this is what we have, and we can see that the mean squared error on this data set is extremely huge, right? And so so that was just one of the validation sets. And yes, question.
So for choosing the types of models that we would compare, is that motivated by like some type of theory that is behind the data, or should we, like, how do we choose which ones?
Yeah. Okay. So the question is, how do we choose which models to even kind of test out and things like that? And the answer is, I don't know. It's complicated, as the answer always is. This was here. I just have one variable. We're just looking at the race time versus the year, and so because I only have one variable, there's only a few things I can do with it. I can like put it into polynomials of different orders, and maybe I didn't try taking a log or anything like that. The data didn't look like I would need to take the log, but you know, that's also an option. You know, you can, I would say it's more useful in the case of like multiple linear regression, which in matrix notation is exactly the same. You just have more columns in your X matrix and more terms in your W vector, and then fitting the different models will be, do I want to include this variable or things like that, okay? And so you could fit kind of competing models where one you're using square footage to predict housing price, and the other one maybe you're using a number of bedrooms to predict the house price, or another one you're using both of them, square footage and bedrooms or something. Or, you know, bedrooms versus bathrooms versus whatever. And so you'll have kind of multiple competing models, and this would be a way to compare the different models where, in that case, the models say, you know, should we use this, this variable or some other variable. Okay, so here, those values came into validation set C, 0.0369, 0.0207, 0.0125. those are these values here, 0.0369, 0.0207, 0.0125, 0.023, 0.038, and 32.8193, okay? And so this is, that's where this column of values came. Again, we fit it to all 4 validation sets, and because the data points that show up in each of the validation sets are going to be different, you're going to get very different values. Okay, so some of these are much lower, much higher than others, and then you just kind of take the mean of these things. Okay, so here the mean cross-validation score is 0.0633, 0.0509 for the quadratic, 0.0376 for the cubic one, and 4th order, 5th order, 8th order, and 17th order polynomial. And we can see for the degree 17, it's quite off, right? So kind of based on this set of 4 partitions, we would choose the 3rd order polynomial here, 0.0376, as the model that we would choose. Okay, because this one has the lowest cross-validation error. The one thing about k-fold cross-validation is that it's sensitive to the values that we put into each validation set. Okay, so I just took the original 28 observations and I shuffled them. Okay, and I shuffled them, and so it just happened to be that these 7 observations ended up in validation set A, these 7 observations ended up in validation B, and so on and so forth. And so if I ran this again with a different seed, we're going to get different validation blocks, and so our cross-validation scores will end up different. Okay, and so if I look at these cross-validation scores, which are just the average of the other 4, okay, so just again looking at this column of cross-validation scores, which are the average of the other 4, again we see that the 3rd order polynomial, the cubic function, still performs the best, whereas the 17th order polynomial performs the worst, and everything else is kind of somewhere around, somewhere in between. So that's what happens here. However, if I changed the seed, okay, another time, and I fit k-fold cross-validation, in this case, it just so happened that when I look at the mean cross-validation score, the 8th order polynomial happens to be the best performing one. Okay, so we see the linear and the quadratic, and then the 3rd order polynomial goes down, and then the other ones do poorly and go up, but somehow the 8th order polynomial happens to do the best. Okay, and we know that this result here, where the 8th order polynomial is performing the best, that's most likely because, or it's because of just some random fluke of how the validation sets got selected. Okay, and because we've done this k-fold cross-validation a couple other times, and we know that the 3rd order polynomial is generally the best, and it's still the 2nd best performer in this set, we can be confident about that. Okay, the issue is that often you're only going to run k-fold cross-validation once, maybe twice. Okay, but the whole idea behind k-fold cross-validation was that it reduced the computational expense, and so you might not know whether this is a random fluke or not. Okay, so that's what happens there. Is that okay? So because there is a random element in how the validation sets go, there's also a random element in the cross-validation scores that you see. Okay, you can do cross-validation with LibraryBoot. So all the way back here, I wrote this huge thing of code, which is fine. But there are functions in R that kind of make it a little bit easier. And so there's LibraryBoot, and in order to use LibraryBoot, you'll use a GLM rather than just the regular old LM model, okay? And then you'll use CV.glm to perform cross-validation. You can specify the argument k for the number of folds, and if you leave it blank, then k is going to equal the number of observations you have, which means it's going to perform leave one out cross-validation. Okay, and then the score is generally the average squared error, but you can also provide it another function to calculate the score cost there. Okay, so I'll run just show how crossvalidation.glm works for you know, a few of the models, and again, if I'm going to run it a few times, and we're going to see a little bit of variation between the runs because the random blocks that get created will differ from run to run. Yes.
Excluding computational expense or time, is leave one out more accurate than k-fold?
So leave one more accurate. That's a little bit hard to say. Leave one out has no random subjectivity to it. Okay, so yeah, if I run leave one out cross validation, because every data point serves as a validation set, if I run it once and I run it again, we're going to get the exact same cross validation score for every single time you run leave one out cross validation. Is it more accurate? Yeah, I guess. You avoid some of the drawbacks where there's kind of a random element at play. But again, it is computationally expensive, and then also you also get slightly. The issue is because when you train your models, you're training it on pretty much every single data point except one. Your models end up looking quite similar to each other, and there's kind of this idea of like how well does it perform on like entirely new data set that you haven't seen, and it I don't know if leave one out does the best at kind of modeling something like that. So anyway, using a GLM, CV.glm makes this cross-validation stuff really easy. Okay, all we do is we just do model GLM. I don't know why I did poly year one. I could have just done year. Okay, poly year one is the exact same thing as year. I think I was just copying and pasting code and just changing the value that was here. Okay, but anyway, you fit your GLM model, and notice that here I'm using the full data set. I'm not using a train or a validation split or anything like that. I'm just going to go ahead and provide it the full data set, and CV.glm will handle the train and validation splitting. Okay, so I just do CV.glm, the full data set again, give it the model, and I say k equals 4, and here's the kind of the cross-validation score. And every single time I run it, I get something a little bit different. They're not wildly different, but there's enough variation. Okay, but they are at least on the order of what we saw in our cross-validation things. We got something on the order of 0.06, 0.068, 0.0627, 0.0633. And we're getting, you know, 0.066, 0.0578, 0.055. Okay, so at least on a similar order of magnitude. Here I'm doing a quadratic model, poly of year comma 2. This is model 2, and I'm just running k-fold cross-validation. I run it 3 different times, and again, we get different values with some variation between them. Okay. And kind of what we're seeing is that the cross-validation score that we get for the linear model and the quadratic model and you know, even the cubic model are are quite within their a standard error of each other. So it's a little bit difficult to say. Okay, and I didn't bother doing it on any more of these models. I figured you guys got the picture here. Okay, and then and here, if I don't specify k equals 4, this will perform leave one out cross-validation, and you can see that every single time I run leave one out cross-validation, I get identical results. Okay, because the validation sets are exactly the same every single time. So, and then with a data set of 28, like you don't even notice the thing running, the difference there. Okay. All right. So if you look up cross-validation on Wikipedia, you get a long article, but I just stole like 3 or 4 sentences from the introductory part. And basically the big picture idea, it's a method to see how well a particular model will generalize to new data, and we're kind of testing the ability to predict new data that wasn't used in estimating the model, to kind of watch out for problems like overfitting. And then, multiple rounds of cross-validation are performed on different partitions. Okay, and again, because as you already know, you can always make your model more complex, and it will do a better job of fitting the training data. Okay, but we don't want to just minimize the error on the training data, but we want to see how well it will do in future data that we haven't seen yet. Okay, and so we kind of give ourselves, it's like a practice quiz using the validation data. Okay, so now we're going to kind of take a step back and start talking about computational methods to optimize the loss function. Okay, so we've talked about cross-validation. Now we're going to go back and we'll just talk about optimizing the loss function. Okay, and so far for this linear regression model, we've just been using this linear regression or multiple linear regression model. We've just been using calculus because our loss function has been pretty easy. Our loss function is just the mean squared error. We take the difference between the actual and what our model predicts. We square that difference, we sum them up, divide by n. Okay, it's a simple loss function, and so it's been easy to find its derivative, even in matrix notation. And so using calculus to kind of solve for this hasn't been bad. Okay. However, in the future, we might have more complicated loss functions. Okay, so the loss function can become more complicated. And we might be able to find the derivative, but being able to solve for where the derivative is equal to 0 might be an impossible task, or might just be really difficult to do. Okay, and so in these cases, rather than trying to come to an analytic solution, we have all these kind of cheater tools that we can use, these computational methods. So we saw, a couple of them in 102A with these optimization functions or optimization algorithms, and we'll take a look at some in this class. Okay, and so the goal is that we want to minimize the loss function, and we do this by trying to find, so far we've been using calculus to take the derivative, set it equal to 0, but now I'm saying that might not be possible, okay? And because we've got a multi-dimensional function, we have to use a multi-dimensional optimization method. So in 102A, we mostly had unidimensional optimization. We did see coordinate descent, all right, and in this class, we will take a look at gradient descent. Okay, so gradient descent is truly a multidimensional optimization algorithm. There's pros and cons, situations where it struggles, but we'll take a look at it. Okay. All right. So the idea behind gradient descent is that the derivative for a function of a single variable, the derivative represents the slope of the tangent line at some point x, okay? This should be a little x over here. When we have a multidimensional function, a function of several variables, the gradient is the direction of the greatest increase of the function at some point x, okay? So it's kind of like a tangent line, but in higher dimensionality, okay? So you can kind of think, if we've got a function of 2 dimensions and the function represents kind of the surface, you can just think of it as the tangent line on some kind of landscape, and it kind of points in the direction of the highest, the quickest ascent, or where it's pointing uphill. And if you take the negative of that, it'll point downhill. Okay, so you've got this kind of this landscape, and the gradient now points in the direction uphill, and the negative of the gradient points downhill. And so the idea of gradient descent is that we're at some location, and the gradient points in the direction of the greatest increase, and we'll just move in the opposite direction, which will be the direction of the greatest decrease at that immediate point, okay? And so that's going to point us downhill, and we take a step down, and we just repeat this process, and we should reach the bottom of the hill, or at least the bottom of some valley, okay? Maybe it's a local minimum and not the global minimum, but at least it'll get us down the hill. So the idea is basically you got kind of this ball, you set it on top of on the surface, and you just let it roll, okay? And gravity will just bring it down, okay? And so the gradient is always going to just kind of point downhill, and the ball just keeps rolling downhill, okay? And so the algorithm is incredibly simple, okay? You've got some multidimensional function, okay, f of w. This is pretty much, in our case, this is going to be our loss function, okay? And we've got it's a function over the values that we want to try to optimize. We start at some arbitrary point w sub n. Okay, so if we're currently at w sub n, then the next value that we're going to be, or the next location, will just be wn minus the gradient. Okay, and we multiply that by gamma, some kind of scaling factor. Okay, either gamma or lambda. Okay, and we just multiply that by the gradient. And then that gives us a new location, and then we just repeat. Okay, so you just, where are you? Where's the gradient? Take a step in that direction. Okay, or take a step in the opposite direction. So the gradient points uphill, just move in the opposite direction so you go downhill. So this is pretty much what it looks like. Sometimes lambda is used instead of gamma, or I mean some other letter. They often show up all over the place. Okay. So there is a package called Library Animation, and it does nice animations and illustrations of this, but it's not really great at other than like kind of the functions it might provide. Okay, so here, let me just kind of load this up. So, so this is going to be the function that I want to optimize. It's a function of x and y here, okay? And it's gonna, you're going to see a contour plotted over here, and then you'll see these blue arrows representing gradient descent, okay? So here it goes, okay? So here is the thing, and it's just taking steps down the hill, okay? So, you know, we started off here, and out here, the slope is steep, so the gradient is large, and so our initial steps are quite big. And as we go down the hill, okay, so you just imagine this bowl, okay, and you can have this. It also creates a 3D perspective plot. So you know, where we start this slope is steep, and so so it's going to take big steps. But as it reaches closer to the bottom, the steps get smaller and smaller and smaller because the gradient is, related to how steep the slope is. Okay, so as you get towards the bottom of the bowl, the slope gets shallower and shallower, and so your steps get smaller and smaller and smaller. Okay, and so so here I just started off at the point -3, -2. I'll just show you what it looks like if I start at -3, -3. Okay, so I'm going to start at this corner, and then, again, it's just kind of moving. It's just pointing down the hill, and I just have it do 20 iterations because technically each step gets smaller and smaller and smaller. It's kind of like with each step you're closing half off, right? And so you never actually reach the destination. Right? Okay. Here's like another function, okay, x squared plus 3 times sine of y, and we've got kind of 2 local minimums, okay? And so if I start over here, it's going to roll downhill, and it's going to end up kind of in this zone, okay? I just have it stop after 20 iterations. But if I start somewhere else, we'll see if I start off at -6, 0. Okay, -6 point something 0. Probably I'm gonna ending up over here. Okay, and so these are just whatever different. Different things, and you can kind of just see how these oh, it's going up. There's apparently another one down here, and it's ending up over there. Okay, so it's just kind of rolling downhill, and it's looking for like a minimum, and so there's no guarantee that you're going to end up at some global minimum. That's one drawback of gradient descent, but it does guarantee that, I don't know about guarantee, as long as the gradient can be found, you're going to be taking steps downhill, okay? And you're basically just giving instructions, keep walking downhill. Wherever you are, look around and walk downhill, okay? And so this is kind of the issue that we have, and we're kind of either starting on this side or this side, and so when we start here, it rolls down into this ditch, but if I start over here, it rolls down into that ditch over there, okay? So that's the gradient descent animation. I guess we'll have to wait till Wednesday to actually do kind of gradient descent ourselves. But that's where we're going to be headed. Okay, we'll end there. You can expect to see homework posted soon. So